Good afternoon. Thank you all for coming to the 48th Annual Lunar and Planetary Science Institute. I'm Eileen Stansberry, one of the co-chairs. I would like to welcome you all on my behalf and my esteemed co-chair, the new director of the Lunar Planetary Institute, Louise Proctor. It's a pleasure and an honor to be able to kick off this plenary session. And because we have a lot of work to do, I'm going to immediately shove into the GSA Dwornik Awards. Jim Ray.
Thank you. Good afternoon. I do have some slides. There we go. It's an honor to stand up here representing the Geological Society of America's Planetary Geology Division. Briefly, for those of you, especially who are new to LPSC, who might not know what GSA or the Planetary Geology Division is, it is over 1,000 of your close friends and colleagues. So if you are not a member yet, 1,000 planetary geologists can't be wrong. So for the 2017 fiscal year, essentially, I am the chair of the division, and we have a management board consisting also of first vice chair Brad Thompson, second vice chair Sharon Wilson Purdy, secretary treasurer Emily Martin, who is maybe hiding in the back somewhere, and past chair Danielle Wyrick, who's also here. And we have two student board members. Mathieu Lepotra from Caltech is our senior student board member, and Elena Favaro from University of Calgary. So except for Elena, all of us are here at the meeting this week. We have a booth down in the exhibit hall. We hope you will come by. This is a photo from a few years ago, but we're in the same place toward the back of the exhibit hall. If you come by, we've got these very awesome pins, which are clearly the hottest new trend in conference fashion, and to have one of those. But we're really here because we represent all of you, or we want to anyway, and especially this particular year, I think many of us feel that it's a dynamic time, to use a neutral term, in our national and international cultural, political, funding situation. And I think what hasn't changed, though, is that we set the tone for the type of community we want to have at our conferences, in our research teams. And what I feel very strongly about is that we must not make any individual or group within our community feel marginalized, either through acts of commission or omission, for the sake of both our science and our humanity. And so I wanted to say that, and if you feel that we are not meeting that standard in any area, I hope you will come and speak to us at the booth. Glad you all agree. You can find out more about what the division does on our website. The URL is here. We manage a number of awards for planetary geoscience. In particular, I would direct you to look at the student opportunities, including a travel grant to attend our GSA annual meeting is in Seattle this year. I hope to see most of you there. The awards, obviously the focus today is the Dwornik. I want to highlight one other award that we give each year to a member of the community who's provided exceptional service to planetary geoscience. Last year, our winner was Tracy Gregg. A few years ago, our winner was Louise Proctor. And because the deadline for nominating your colleagues who are deserving this award is only a few months away, please be thinking about who would be good candidates for it. Okay, so moving on to the Dworniks, which is the main event. We've been awarding this since 1991, possibly before some of the younger students were born. And we give an award for the best presentation at LPSC divided into graduate student and undergraduate student categories and by oral and poster presentations. So we have most of our winners from last year here, and we have a plaque for each of you, and Brad Thompson, who made the final selections for this year, is going to hand the plaques out. So our first winner in the graduate student category for best oral presentation at the 2016 LPSC is Michelle S. Thompson from the University of Arizona. Congratulations. And then we don't always do an honorable mention, but we had a very close second this year in the graduate oral category, and that is Mathieu G.A. Lepotra from Caltech. Congratulations, Mathieu. In the graduate poster category, our winner for 2016 is Cameron Mercer from Arizona State University. Congratulations, Cameron. And for honorable mention, best grad student poster, we have Lauren M. Joswiak from Brown University. Congratulations. In the undergraduate category, we had one oral presentation last year that was far and away the best, and that was by Danielle G. Neighbor from the University of Arkansas. Danielle herself is not here, but her second author, Sandeep Singh, is here to accept the award on her behalf. And finally, undergraduate student posters. We have a Best Poster Award this year to Julianne Sweeney from the State University of New York at Geneseo. And finally, an honorable mention to Michael J. O'Shea, also from SUNY Geneseo, who is not here in person, but a round of applause for him anyway. So, the over 100 Dwornik applicants that we get every year could not be sifted through without the volunteerism of hundreds of judges at this meeting every year. Thank you so much for what you do. If you're not judging Dworniks this year, what's up with that? For next year, you can sign up by checking a box when you submit your LPSC abstract, and then you sign up for the individual presentations you want to judge online. You can contact our second vice chair for more information. This year, that's Sharon Wilson Purdy. And we do have one tweak to the Dwornik process this year that Brad Thompson kind of masterminded, and so he has one slide on that he wants to explain to you all.
Thank you, James. Just real quick, this process has improved over the years. We've moved from a paper-based form to online submissions to the judges, and a number of years ago, we had to change the actual donation GSA to open it to international students at U.S. institutions. This was a long-standing tragedy. Actually the incoming director of LPI was disallowed from competing when she was a graduate student. But another important change we instituted this year is, so it's great if you win the Dwornik Award, hooray, but the judges put a lot of work into their feedback and comments, and that doesn't often reach the students. And so what we've done this year is we've divided the comments form into two parts. There'll be one part that'll actually go to the review board, and one comment there for the student presenters, anonymously, and I'm confident that our judges can provide polite, respectful feedback to the students, and hopefully that'll go smoothly, but it will make it a better experience for all participants because they'll get some feedback to help improve their presentations, which is always a good thing. So, thank you.
And now to present the 2017 Perazzo International Student Travel Award is Mark Sykes.
Thank you. 6 years ago, we lost a valuable member of our community, Betty Perazzo, noted expert in impact processes and astrobiological effects of that. But Betty was also very big on setting up international collaborations promote research across a wide variety of projects. And so after she died, we set up the Peraza Memorial Fund. There was a question about how to use those resources. And in consultation with her husband and family, we established the Peraza International Student Travel Award, in which we pay for, we give a certificate and $2,000 to a non-U.S. graduate student to come to the U.S. for a conference, and for a U.S. student to go to an international conference outside of the U.S. And so I'd like to present the first of our 2 awards this year to Frances Butcher, who's from Open University, for her work on eskers associated with extant glaciers in mid-latitude Graben on Mars, evidence for geothermal controls upon recent basal melting of glaciers on Mars, which she'll give tomorrow afternoon. And thank her very much.
And to present the LPI Career Development Award winners is the incoming, the new Lunar and Planetary Institute Director, Louise Proctor.
Crowd looks a lot bigger from up here. Okay, so it's my great pleasure, as my first official duty at this meeting, to read the names of the 13 recipients of this year's LPI Career Development Award. So this is a travel award that we give out to anybody from any nation can apply. And so this year we had 73 applications from 13 different countries. So really good showing. And the winners come from the UK, Canada, Germany, the Netherlands, and of course the US. So because we've got quite a lot of them, we're just going to read their names for now, and we'll celebrate with them a little bit later. But very happy to congratulate them on getting this award. So they go to Kevin Cannon from Brown University in Rhode Island, Edgard Siko Steenstra from Vrije University in Amsterdam, hopefully I butchered that too much, Ali Bramson from the University of Arizona, Oriel Ray from Imperial College in the UK in London, Mallory Kinchik from North Carolina State University, Gerrit Bood from Westfälisch Wilhelms University in Munster, Elise Harrington from the University of Ontario in Canada, Stephanie Quintana Bucci from Brown University in Rhode Island, and Vivian Sun, also from Brown University, Aria Bina from Western University in Canada, and Christy Cordill, also from Western University in Canada, and then Josiah Lewis from Washington, WashU in St. Louis in Missouri, and Tim Hahn, also from WashU. So congratulations to all of you. Let's give them a round of applause. And with that, I'm very happy to pass on to Walter Kiefer from the LPI, who is going to introduce our Masursky speaker.
Okay, well, it's a pleasure to be here to honor Dave Smith. Dave was my postdoc advisor at Goddard way back when. He's been an important person in this field for a long time. Dave got his education in England. When he came to the US, he began work at the Goddard Space Flight Center on various geodesy things. He's now affiliated with MIT. While he was at Goddard, 2 big contributions that some of you know about, but maybe many of you don't. He was the person who conceived of and led the development of the Geodyne program. Those of you that do gravity, all of your gravity harmonic coefficients come by magic from that software. Okay, not quite by magic, by a lot of hard work actually. In addition, Dave was the project scientist for NASA's Crustal Dynamics program in the 1970s and 80s, and affiliated with things like the LEGIO satellite, measuring the rates of plate tectonic motion in literally real time. For many people, those 2 accomplishments would have been enough to call it a great career. Dave wasn't satisfied with that. He made the transition to planetary geodesy in the mid-1980s, and we've all been the beneficiary of that data ever since. He'll talk to us mostly, I think, about laser altimeters today, things like MOLA, the Mars Laser Altimeter, LOLA, the Lunar Laser Altimeter. But he's also been involved in gravity work. Most recently, he's the deputy PI of the Grail mission, which has revolutionized our view of the moon. just two other things as a measure of the success of his career. One is that if you, JGR Planet celebrated its 25th anniversary last fall. Associated with that, they put out a list of the top 10 all-time cited papers in JGR Planet's history. I wasn't really surprised to find out that Dave's paper on MOLA observations of Mars led the list, and he spotted people 10 years in the process. Many of you contributed to those citations because of the importance of that work. And the other thing I'll highlight is that AGU recognized his importance of his contributions both to planetary geodesy but also to terrestrial geodesy as the Charles Whitten Medal in 2012. Dave will talk to us today about planetary topography from laser altimetry. We're all in his debt. Dave.
Good afternoon, and thank you to the organizers for inviting me to give this talk. I really appreciate the honor that's bestowed here.
Sorry?
Okay.
Sorry. It's not in my control.
He's going to keep me on time here. It's about laser altimetry, it's about topography, but I'm actually going to talk a little bit more about the whole field than just the topographic aspect. I'm interested in the dynamics and things of that kind as well, but it'll all be associated with this kind of measurement. Okay, the screen shows you actually one of the earlier kind of images we put together from the MOLA data at Mars, which is, as you will all recognize, is the floor of the Hellas Basin on Mars, and it shows the structure of the floor, and you can see the flows that have taken place and things of that kind, all of which comes from the use of the MOLA altimeter data. So, moving right along, laser altimetry goes back to Apollo, but then there was nothing basically until about the early 90s. Since then, there have been a number of instruments that have been flown to the planets, particularly the moon, and some asteroids, and these are shown on this to a large degree on the chart here. This is Apollo, and then you see the other ones down here that we've been working on recently, from the Clementine right down through the ones at the moon, then the international ones here for Selene, Chang'e, Chandrayaan, etc., and by other nations. So the field is really getting quite developed, but many of these instruments are different, and I'll try to show something about that, at least in the course of the discussion today. So moving right along here, okay, a laser altimeter is in fact, in my opinion, a geodetic tool, and it's a tool that you can use in a number of ways. And it can provide the range to the surface very accurately, what we call the bounce point, if you know what I mean, with high precision. And this is really what it measures, or at least that's the first thing it measured. And it can, if it's provided in a sense around a planet almost continuously for, because it's an instrument that is essentially on all the time, as it was at Mars and has been at the moon, when in the right altitude and so on, that you start to map out the surface in a geodetic sense, in which you kind of get the radius of the planet, if you like, to centimeters or tens of centimeters, depending on the orbit and a few things of that kind. But the point is, it maps out this structure, and so with good orbital knowledge, you can actually get a reference system out of this, and I will say something about that in a moment, at least in terms of examples. Okay, and of course, by the nature of it, having a small spot size and things of that kind, that it really benefits from working with other instruments. And so the obvious choice is a camera, a stereo camera, where you can put the whole package together for the planet, and I'll show you some benefits of that in the course of the talk this morning. So how does a laser altimeter work? Well, it emits a laser pulse. 1064 nanometers are the ones that we've been largely using now for 20 years or more. It hits the surface, it bounces back up again, as you can see in the chart on the side here. Time is recorded, and it measures the round-trip travel time to give you the distance of the surface to, usually 10 centimeters or some number like that. Okay. Then, in addition to that, you need to measure, or we do measure, the area under the return curve, which, oops, hold on. Under the under the curve here, which is what the pulse looks like when it comes back. Okay, distorted by the surface. But that tells you something about the surface, and so the ratio of that area compared to the output from the laser initially gives you something about the reflectance, and that's what one can get to, something like about a few percent. Okay, so beyond that, you'll notice that this particular pulse is much wider than the outgoing pulse, and that spread of the pulse tells you something about what's going in the area that's illuminated. And typically at the moon, for example, it's a 5-meter spot that you illuminate, and as you get some roughness in there in terms of topography, that pulse got spread out in time actually as it comes back to the spacecraft. So you can learn something about the topography within the footprint. We call it roughness, and that's generally speaking about a nanosecond, 30 centimeters, 20 centimeters, in that sort of region is about the best that you can reasonably do, at least at the moment. Okay. Global topography, as I've said here, is tried to say here, and it helps to define the coordinate system. So when we first went to Mars, we really did not know very well where we were. I think I can say that in many cases we were many, many kilometers off from where we thought we were. That's because there hadn't been a systematic analysis of any observation or any observations made that we could analyze to provide a detailed understanding of where everything is on the planet. And so Mars was the first one of that, and I'm delighted to say that that one tends to be still the state of the art at the present time, and will be until we actually get a lot more altimeters of some kind or other there to actually improve on this. And it has been argued that, well, you've done Mars, let's move on to somewhere else, and to some degree that is true. And I'll come back to the quality of this in a moment. The same things happened to Mercury, except that there we can only do the northern hemisphere because of the altitude and of the spacecraft in a highly eccentric orbit. So but essentially you do get the same kind of shape information all over the northern hemisphere, and I'll explain that a little later. And then there's, of course, the observations of Eros. That goes back a long way. The first asteroid I think that anybody ever basically visited. A great mission in many respects, and a very small object, and you can see the picture there that you can derive from the ranging system that was on board. And then, of course, the moon. I won't say anything more about the moon today. This is the one that we've spent most of our time at. We've been there for 8 years now, I think it is, or very close. And it really has defined the moon in terms of a geodetic sense about where we are in collaboration with cameras and other instruments to great detail. Okay, so if you want to build a planetary coordinate system, or if you want to know where you are, you need to define yourself with some body fixed coordinates. And the laser altimeter is ideal for this. Once you know the pointing of the spacecraft, once you know the altitude of the spacecraft, once you have that geodetic ranging to the surface, you can start to say this place is X, Y, Z, or is it this given latitude and longitude. You put the whole package together, and now you have a framework. It just maps the surface. Mars, we started off with this at Mars when Mars mission, Mars Observer, selected the laser altimeter, Molar 1 as it was at that time, to go to Mars. The job was, in fact, to understand why various measurements collected by Viking and so on just did not fit up in terms of pressures and altitudes and things like this. And we needed to last 30 days, and we were anxious. We'd never done anything like this before. In the end, we're talking about many years later, because Mars Observer was lost. We had to refly the mission. We actually lasted for over 3 years, and that's what produced the topographic shape and map and everything of Mars as we have it today, and that many of you have in fact used. So you first of all, you do that part of it. You get everything in a system, one system on the planet that everything can relate to. The other is, that's in some ways more interesting part, is that is never fixed in itself. The body moves. And so the reference frame part, in the way I work on it anyway, is that you take that coordinate system, and if you're really interested in what the dynamics of the planet is doing, how it's flexing and so on, you look at the variations in the way the coordinate system moves. And that's where you've got this grid, and you can watch to see how this grid moves up, down, sideways, twists, etc. And at some level, this happens on all the planets. And some degrees, like the moon, it's very, very small moon. At Mars, it's much larger. Okay. Am I going too far? Hold on a moment. Excuse me, I have to go back. Okay, no, we're right. Okay, so the polar caps of Mars are fascinating features in many respects, and many of you know them much better than I do, but we spent a lot of time actually measuring them over time, and these are the two plots that we often use to what they look like topographically. And these are bodies which are, you know, at the poles of the planet, but they're about 6 or 7 kilometers difference in altitude. One is very high, that's the South Pole, and the North Pole is much lower, it's in a much more kind of a depression area. And you can see the structure of the two polar caps there quite nicely. And I wanted to show you, if I got this right here, this little area here is about 100 kilometers square, very approximately 100 kilometers square. And on the next chart, I should be showing you, yeah, this is what it looks like. So when you take the altimeter data and blow it up, if you like, to its full resolution on the surface there, and the resolution of Molar was about 100 meters, maybe 150 meters, it was that sort of order, okay? You see this kind of structure in a very small region, and this is a region where, frankly, sunlight is rather weak. Okay, it's always towards the horizon. You can't get down in the crevasses, and yet here you can see, you can get right down into the structure of this crest here, this very small area. You can see the scratches on the surface, which we believe is partly layering and partly associated with the movement of a glacier at some previous time, all coming out of the fact that you kind of know and have co-registered everything. Thank you. Okay. So, moving right along. Okay, but the CO2 deposits itself on the pole, and it looks like this in terms of the brightness of the surface. So if you look at this now, this is early winter on the south pole of Mars, and you can see the brightness here. This area here is what we call the stealth area. This is all done actually by reflected sunlight. There's something called this, we call this passive reflectivity, and then and so the reflection doesn't actually come back to the spacecraft. It kind of goes, it's a specular effect as far as we can tell, goes off into the distance. So we almost as if we're looking right through it. But actually a few months later, the cap has got smaller where the CO2 is condensed, for example, and that's what it looks like. Okay, and we follow this throughout a whole year of it. You can see it coming and you get glow on both the poles. Okay, then there's the molar footprint roughness work that Greg Newman just actually provided this chart to me just a matter of days ago when we're trying to convince Greg to reanalyze some of the molar data. And the interesting thing to me is that we've talked about the spreading of the pulse. Okay, well, he's looked at that, as many people have, but this chart here shows very nicely when you're looking at the North Pole of Mars that you can see this region here, which is very rough being 5 or 10 meters on the scale of about 100 meters. And you can see over here the actual mapping of the North Polar Cap here, which looks relatively small, but this region over here is very rough. And then you look at the topography itself, and generally speaking in topography, it kind of looks fairly smooth. We suspect that this actually, with this location, is really associated with a part of the cap that was once upon really part of the cap. As of now, for some reason or other, it's changed, and the action has moved more to in the center of this region here, as distinct from over there. But we don't know the entire reason for that, but that's what the observations do suggest. Okay, moving along. Yes, you can actually see the increase in the altitude of the cap. So you get a shape of the planet, then you look at the polar regions as a function of El Sabas, that's the time, if you see what I mean, of the year, and you can see the increase in the ice or the snow or whatever the surface is throughout the winter season, then it sublimes back down again, and so you see there's about 1 to 2 meters, maybe, I think it says on there's about 2 meter variation at each of these poles. And this was, this is an average around the pole. We had to average it all the way around to get kind of what I would call fairly sensible answers, and it's not clear that the pole is that even, but anyway, this is what it turns out to be. So we're seeing that we saw it very clearly. We haven't been looking at it recently. And we also saw clouds. Didn't expect this. In fact, we argued beforehand whether we could see clouds, and we in fact did see clouds, much to my surprise, I have to admit. And so here are a couple of tracks in which the altimeter is coming along here. These are natural noise points, one in about 1,000 are planned to be just noise, okay? Then you see this structure occurring here, and on another track the same kind of thing. And the interesting thing about this one here is, we call them nighttime clouds, is because that dotted line that I put on there is in fact sunrise. And so these can't be observed actually during the day, they're not there. but at night time you can, and the altimeter sees them day or night. He doesn't mind. We see the clouds. We see the clouds quite clearly, actually. And I think this is the precipitation that actually falls onto the cap. Okay, Shackleton. Well, I want to say something about Shackleton because this is the moon. I have a lot of data about the moon. It's an altimeter with 5 spots showing down in the corner here, and it's been mapping now for 7 years, I think it is. This is actually a picture of the polar cap. All of it is Lola data. It's just imaged in a way to make it look like an image. In fact, it is. There's nothing strange about it, except the blue in the inside. That's not a nuclear explosion. It's just the way we put it in there so that you could see what the beautiful circularity of that polar cap, a polar crater, is about 21 kilometers across. So moving on, this is what it looks like in detail. The interesting part about this is it demonstrates the capability, I think, here in terms of showing the topography beautifully of this 4-kilometer deep crater. It shows the roughness right along the ridge, the rim of the crater here and on the floor. And then when you blow up the floor, instead of looking at I think it looks like the face of Shackleton on there. When you blow it up, you see in great detail here that there's a mound in this region here, a few hundred meters high, and a slump area on the side over there. So you can really get detail into it. Remember, this is in permanent shadow. You can never really do any optical stereo kind of work, and there are no shadows. Okay. Okay, moving right along. These are looking at the South Pole now, topography and slopes and so on. 2 nice pictures. I will move on from this to the work that Jim Head did when you've got a data set like this, it's kind of uniform everywhere. You can mechanically arrange for things to be done, like you go in and search for craters. Okay, you can let the software do the package for you, and you know that each crater is as well defined as the other, okay? And the net result is that you actually get a map of things like this. And Jim managed to show, and he looked at this, that in fact there's a distribution across the moon in terms of where the densities apply, and therefore where the younger craters are, where the impact basins are, which have kind of smeared out the earlier craters, for example. And so, okay, so I'll move. Yeah, okay, let me move on here. So Erwin Mazarico took that kind of data set, in fact, all of them, and said, well, let's look at the shadowing region that's going on here. And in fact, what you see here is a very slow-moving set of North Pole and South Pole, and the image, and you can see the red spots are the shadows. Okay, this is the permanently shadowed region. The sun, in our lifetime, let's put it this way, doesn't see the bottom of those. Okay, those craters, and so they're there forever. Now, okay, forever being as of today. Anyway, now what Owen has also done is once you've got this digital map, you can move it backwards and forwards in time, because as the moon moves in its orbit or as the obliquity changes. And this shows you what would happen if in fact, since the moon is now at about 2 degrees obliquity, something like that, if in fact the obliquity were 10 degrees, which it almost certainly was sometime in the past, there's no longer the red spots on there, they're just the yellow ones. The small yellow ones are left, all the rest are gone. And if in fact you went to 20 degrees, which is in the blue, then you're left with essentially just about Shackleton and 1 or 2 other small craters here which have blue in them. So if in fact being in shadow is important for the understanding these regions, it's quite likely that they were not always in permanent shadow. Unfortunately, we don't know what the obliquity history of the moon is like in enough detail to know when this has occurred and how long they've been in shadow, but it's changing. Okay. If you've got the shadows, if you've got the shape, you can also see how much light gets into a crater. And this is important for others who are looking at starlight and how important it is when you're trying to do the gardening inside a deep crater. How much of the sky do you see? How much can you get in? And so this chart shows you that, with the deep red, you can see the whole horizon. Okay? That's even in the bottom of some craters. But there are other places, and Shackleton's the perfect example here, where in fact you really just don't see anything. You're just down here to just that part of the sky that's immediately above you in this 4-kilometer crater. So there's much less gardening and much less kind of impact from radiation and so on can actually get into that surface. Okay, Mercury, very similar. We can only get to this part of the planet. You've seen the chart over here before. 1,800 kilometers we've ranged to the surface of this planet to get its shape, to get a feel for it. And the important thing about this, I think, is that as we move... Oh, okay, I'm skipping around a bit here. But when you look at the water ice, interestingly enough, increases the reflectance of the surface. And this is what it looks like at the moon. But Shackleton there is a little bit of a misleading for us because we think the bright redness there is in fact associated with the young surface of the crater itself. But the green is likely to be some presence of water, and it has to be a micron thick, that's all less heat. Okay. So you can see it's there, but if you think the next chart goes to Mercury, if you go to Mercury, it's a little different. You still get something at the poles, but as you move towards the poles, it actually gets darker. These are craters and regions there which have got darker, and then when you move inside 85 North, they suddenly get bright again. And apparently the explanation is that outside of 85 North, it is too warm. It's above 100 degrees Kelvin, and the water is not stable. And so it gets away. There's water probably underneath, but not on the surface. When you get inside the 85 degrees, approximately that level, it's cold enough for the water to remain on the ice surface, and so it looks much brighter. Okay, I'll skip this in the interest of time. We do passive radiometry, which you can do, but I will move along because we're a bit short. I wanted to say something about stereo and altimetry. Ideally, if you want to see a whole planet, you don't just see it with...
2 minutes to wrap.
Thank you. You don't just see it with the laser altimeter, or you do see it, but if you want to get down to detail, you put in some imagery, in particular stereo imaging, you put them together, and you can have the whole globe. And so what you see here is hang on a moment, sorry. What you see here is a region of the moon which is just the Lola data, and you see it's not quite as well defined. When you add to it the terrain camera data from Selene, which is a 10 meter per pixel stereo system, you see a much better picture of it, and about those have been combined together to produce what I consider is the best topography of the moon between about 70 north and about 70 south. From the combination of these two data sets, and I think they will remain the best until LROC finishes its 2 meter per pixel imaging of the whole moon. Then the same thing will be done with that. Okay, and Stark from Alex Stark also did this for Mercury, and he merged the two data sets of the cameras and the laser altimeter, and the net result was he was able to actually, in a cycle, grab hold of the planet and actually see that part about the reference frame moving. And having done that, he was then able to produce numbers associated with the rotation of the planet, its obliquity of a couple of arc minutes, for example, and the actual libration that takes place, because Mercury does librate on its axis. So this is the other end of using the laser altimeter. It helps immensely to have the stereo with it. You've now got a complete planet, lots of points you can look at. And okay, finally, I will move on quickly to this. There is a real shape of Mercury determined from the altimeter, plus the occultation measurements, which are the only ones we can get in the southern hemisphere. And that told us that Mercury was flat at the north, that we knew about, but it was also flattened in the south, but not very much. It's predominantly a spherical planet. And okay, and the last thing I did want to say is that I was very pleased to be able to do and see the growth in the ice of the poles of Mars, a decade and a half ago. But just recently, when Masursky and Mike Barker at Goddard have looked at the Lola data at the moon and have been able to pull out this very small tide of about 5 to 10 centimeters as a result of the moon moving around the Earth, and it's the distance changing, so the moon pulses very slightly at the rate of about 5 centimeters or something, which have been pulled out, and I think quite a remarkable achievement from the data. And I think, the last chart was how well do we know where we are? This is the, I'll put this up here because I didn't want to deceive everybody that we know where everything is on any of the planets that well. Interesting enough, when we put the table together, Mars and Mercury, at least in the northern hemisphere of Mercury, we probably both know them to a location on the surface to 50 to 100 meters horizontally. In the coordinate system that we've established for Mercury, the radius is not as good at Mercury as it is at Mars, and that's because of the orbital uncertainty associated with where we are. We know the range of the surface, but we don't actually know the altitude of the spacecraft at some of these times. So, and eventually the moon, of course, we know the moon better than anything else. I think we're at 10 to 20 meters anywhere on the surface of the moon, basically, and a half a meter in the radius. These are round numbers, but they may be better, they may be a little worse. And finally, where do we go in the future? Well, don't have time to go into the future, but there's a whole group of instruments and ideas about landing lidars, and some are on their way to bodies right now, such as the OSIRIS-REx, which will actually have a scanning lidar on the surface, so we'll be able to measure carefully the shape of the body, and then it will come down to essentially almost a landing situation. Grab the surface and go away. That's a different kind of LiDAR, only works normally under short distances, a few kilometers maybe, but it's a different kind of work, and it's the kind of thing that's going to happen a lot in the future. And it'll have to happen at Europa, hopefully, if in fact we go to Europa with a lander. It's going to need something like that. Tough technology, if I might say so, at least to get the kind of quality that is needed for something like Europa. And then there are multi-wavelengths. We've only talked about one, or used one wavelength so far, but multi-wavelengths are able to sort out all sorts of things. One of the examples is, of course, sorting out the water on the moon, putting 2 or 3 wavelengths. You'll be able to monitor what is going on with a laser altimeter, giving topography roughness, as well as what the presence of the water is at that time. So I think, and that should be my last chart, except for a thank you to the teams on MOLA and LOLA and NRL and etc. who've acquired all these data and enabled me to talk to you about it today. And this is the work of lots of people. It's not mine, but I'm part of that team. But it's been a lot of work by other people, and I do appreciate them very much. And I try to acknowledge that here. Thank you.
We have time for about 5 minutes worth of questions. Please use one of the mics. Well, that's why I want you to use the mics. Okay. Anyone at all? Okay, then let's thank Dave again. The other sessions will start at 2:30. We have to leave this room temporarily, both sides of it, so that they can make it back over for the 2 separate ballrooms. Thank you.